The topic falls over the operator formalism of the quantum mechanics. Somehow it is a mathematical tool we discuss in quantum mechanics. I hope you can support. Just subscribe my channel and hit a thumb button. Okay, let's move ahead. Today, why I say this class gonna be more important to the student is today I'm gonna discuss about three major important questions, probable questions for the examination within a same video. Single video of the 5 minutes where you will be able to solve three different questions of unitary operator. First question will show the norm of the eigenvalue of unitary matrix is 1. Second, will show eigenvalue of a unitary matrix have modulus 1. And third, will show the eigenvalue of unitary operator are complex number. And these all three questions are very important from examination point of view. So let's get started. Before going over here, first of all, we need to understand what is adjoint of a matrix. Before going to adjoint of a matrix, the way is to understand the transpose of a matrix. What is transpose of a matrix? It's just a high school level mathematics problem. If the problem is of a matrix with real elements. But this time we are not going to discuss only about the matrix with the real elements. The transpose is simply matrix which you obtain just after interchanging the rows with column. For example, I would like to take an example here. Just write a matrix is I, 3, 2i and 2i plus 1. This is my matrix. So I'm going to write its transpose at first. So transpose of A is written as A transpose, which is a new matrix with interchanged row with column. So I'm going to change this row into the column in the new matrix. So it is I3. And again, I'm going to change the second row to the second column, like 2i and 2i plus 1. This is my A transpose. Now, to get the adjoint of a matrix, we have to take the complex conjugate of the transpose of a matrix. So let me write adjoint of a matrix A. Adjoint of a matrix is written as adj of A, which is the complex of the A transpose, complex conjugate of A transpose. So what I'm gonna do is I just change the complex part. If the matrix has every element real, then adjoint of A becomes equal to the transpose of a matrix A. However, if there is any complex element inside the matrix, then you just have to change their sign to make it a complex conjugate. So I change its sign because I is a complex number. I change its sign to negative minus 2i. It is also complex. And 3 is real, no need to change. You change the sign minus 2i. Well, and loss 1 is real, no need to change that sign. This new matrix is the adjoint of the matrix A. This is the way to write adjoint of a matrix. Well, if we write A, then its adjoint is written as a dragger. We pronounce it as a dragger. Your U is in a matrix, U dragger is in its adjoint. So if we multiply a matrix with its adjoint, and it is equal to identity, or if you multiply an adjoint of a matrix with its original matrix, then also it becomes identity matrix. Then the matrix is called unitary matrix. Here we're going to discuss about the unitary matrix and its eigenvalue equation. For example, I'm going to write eigenvalue equation for that unitary matrix U. Unitary matrix, and this psi is its eigenkate, lambda is its eigenvalue. This for equation 1. Well, then I'm going to write its a complex equation by using a property of the operator formalism. If you have a operator A with state psi operated from the left, this is equals to the kate psi and a dragger. this concept I'm going to use to write the complex equation of the equation 1. So let's look. Well, it takes this from you. This you actually should be here down, but because of the type error, it's here up. So it's not so big deal. So you can see over here, this u becomes on this side. It's a u dragger, and this lambda takes its conjugate form, and bra becomes skate in both the sides. Now I'm going to multiply equation 1 by equation 2 from the left. I'm sorry. Yeah, it takes this form. But as we know, this is equals to the identity matrix according to the definition of unitary matrix. Sorry, yeah, the unitary matrix. This u dragger and u becomes I, so we can write this equation reduced to this form, and we can bring this side outside. We can bring a right hand side to the left hand side. We can take common, and for this equation for to be valid, either this part should be 0 or this part should be 0. But this part cannot be 0 because it simply represents a scalar product with itself. So this part should be 0. It means eigenvalue of a unitary matrix multiplying with itself is equals to the 1, or this form. Here, lambda star and lambda, they are complex conjugate of each other. So still we don't know whether a lambda is complex or not. If it is lambda is real, then its complex conjugate should be equal to it. There will not be any complex conjugate. The real number has a complex conjugate equals to itself. However, if it is a complex number, then it will have its a corresponding complex conjugate. This time we are not sure whether lambda is real or complex. So I'm gonna take a more general form of the lambda, and that is a complex a plus ib. It contains both real as well as imaginary parts, just for a check. Then its complex conjugate becomes a minus ib. We just change the sign of the imaginary part, and to get a lambda star equal to lambda, I multiply these two expression. It ultimately gives a square plus b square. But from this expression, we know lambda star into lambda equals to 1. In this expression, a square plus b square is actually the norm of the lambda. So from this expression, it is proved that norm of the eigenvalue of unitary matrix is 1. We proved the first theorem, first question. Now, similarly, I'm going to take next example. Let me take a lambda equal to e to the power I theta. Then its complex conjugate becomes e to the power minus I theta. Just changed the sign of the the complex part. Then when you multiply lambda with lambda star, it gives 1. Here also norm becomes 1. Next example I'm going to take for this. You have lambda equal to cos theta plus I sine theta. Actually, this is the form. This is the formula of e I theta. But this is in the trigonometric form of the exponential e I theta. If you have lambda equals to this expression, then just yeah. Then its complex conjugate lambda star becomes theta minus I sine theta with negative sign here. Then if you multiply these two, we get again norm a square plus b square equal to 1. That should be 1. Here also norm is 0. So we are done with number 1. And from these two expressions and this one, what can we say is lambda is not real always. It can be complex also. So we proved the second theorem. Second question is that lambda is complex number because it is valid for all complex. We took 3 cases. So what I do here is this lambda star and lambda, if we keep in the single modulus, this gives the norm from this expression you can see over here. So I write the norm of lambda. This expression is the norm of lambda. Norm is equals to 1. And from this expression, I can derive this one. I just took a positive sign, a magnitude. So magnitude of lambda should be 1. Now I proved all 3 questions. The norm is 1. It's complex. Lambda is complex. I mean, an eigenvalue of a unitary matrix is complex, and here the modulus of the eigenvalue of unitary matrix is 1. So here we proved all the theorems. I hope you are doing good. Keep it up. Study hard. Thank you very much.